Okay.
So Raoul, you can go. So Raoul will tell us about active Brownian heat engines, and he's speaking from Delhi, I assume, in India. So Raoul, you can go.
Okay. Yeah, thanks very much for giving me this opportunity to talk about some recent work that we have been doing. So most part of this work is done with my PhD student, Rita Muzumdar, and of course Arnab, who is the organizer of this meeting, and and with some other collaborators. So the title of my talk is Simple Models of Active Brownian Heat Engines, and I am at IIT Delhi. So I will start. This is the outline of my talk. So I will briefly discuss what mean by stochastic thermodynamics. Of course, it has been discussed quite extensively in this meeting. I will talk about a little bit about heat engines in general and miniaturizing them and so-called Brownian heat engines, and also talk about active Brownian heat engines. And I will summarize this first part. And if time permits, then I will discuss about some general results related to underdamped active heat engines. And this is the work done with Victor Holubeck, who is probably also attending this meeting. So this is the theoretical analysis that we require, and that is because what you have here is yeah. So consider a Brownian particle, let's say in one dimensions, and it has been acted upon some external time-dependent force. And if you let it evolve, it will for some time, it will go from some initial state, and it will just go randomly from as the time progresses. And if you look at another trajectory of this particle, it will go somewhere else. Okay. So the idea of this stochastic thermodynamics is basically to ask this question: is how much is the amount of heat exchange between the particle and the bath, and if there is a time-dependent external force or potential, then how much is the amount of work done on this system. So here what you see is that I can write down an underdamped Langevin equation, and what I can do is sorry, I don't know why it's okay. Write down this equation, and if I multiply this equation by let's say the velocity of the particle and doing some algebra, I can recognize certain terms. One of them is the work done, and other is the heat exchange. Work done obviously contains the time derivative of the external time-dependent potential, explicit time-dependent potential, and heat contains basically the force due to the heat bath into the velocity. So this is something like a heat current or energy current, and it's integrated, and hence you can recognize them as work done and the heat exchanged between the bath and the particle. And you can write down the first law of thermodynamics using this equation, where delta U is the change in the energy between the final particle position and velocity minus the initial one. And as you can see, these two trajectories are quite different from each other. The value of the W and the Q will also vary as one goes from one trajectory to the other. So this is a brief what do you mean by stochastic thermodynamics. Though this is the first law that we understand from thermodynamics, this law holds for each of such stochastic trajectories. Okay, so another part that I will try to connect with the stochastic thermodynamics is that of heat engines. We know that in usual thermodynamic heat engines, you have a working substance. You take it in contact with a heat bath at higher temperature TH, and then you remove it and take it in contact with a temperature bath at a lower temperature. And if you do this process properly and cyclically, there is a finite a way to extract finite amount of work, and you can make this work like an engine. So the very famous engines are Carnot and Stirling. Carnot, of course, is an idealized version. It's quasi-static and takes infinite time to run. It gives you the maximum efficiency, which is nothing but 1 minus the ratio of the cold to the hot temperature. And if you calculate the efficiency at maximum power, is known as the Curzon-Ahlborn efficiency, which also has an elegant expression, which is 1 minus the square root of this cold to hot temperature ratio. Now, the idea is if I start with a very big thermodynamic engine and reduce its size to a microscopic one, as you can see over here. So this is some kind of a steam engine, and I have reduced its size, so a macroscopic size to a microscopic one, and want to study whether if I apply a Carnot-like protocol to such microscopic engines, what happens, and do I get Carnot efficiency and so on. So before we proceed, I will try to give you a representative papers which have been published in last 10 years or so, and all these papers are experimental papers, and what they do is so this miniaturization of the thermodynamically large engines is now known as the Brownian heat engines, and they trap a colloidal particle with the help of an optical trap. So optical trap, if you trap this particle, it acts as if like a harmonic potential, and it will trap the particle in it. And at high temperature, you do this expansion by changing maybe the intensity of the laser that you have in your where this particle is trapped, and then you quench it from hot temperature to the cold temperature. So this is something like an isothermal expansion. This quench corresponds to some adiabatic expansion process, and then you again reduce the trap strength at a colder temperature. So this corresponds to isothermal compression or contraction, and suddenly again increase the temperature from the T cold to T hot. And so this kind of mimics the Carnot or Stirling protocol that we have. And as you can see, as discussed earlier while discussing this stochastic thermodynamics, since the trajectory is stochastic, the amount of work done and heat exchange in one such cycle will of course be fluctuating quantity. So what you need to do is you consider this system, drive it for large number of cycles so that it reaches a steady state, and try to calculate the work done, average work done, and average heat exchange. These things we don't worry in thermodynamics because the fluctuations about mean are negligible. But in case of a single Brownian particle which is trapped inside this trap, harmonic trap, the fluctuations dominate, and you need to worry about those fluctuations. The second part so these papers deal with what are known as passive Brownian heat engines, similar to the one done by Beschinger in about 11 years back. So recently, there have been also some studies that the passive engines contain this Brownian particle trapped inside a harmonic potential, and it is kept in certain medium. And that medium basically provides the thermal fluctuations because that medium is at some temperature T. Now, recently there was a study where this bath also contains certain active entities. For example, this contains bacteria, which are active quantities in the sense that they have a kind of a persistent motion. They move, they do a random walk, and then again move and keep on doing this. So the fluctuations experienced by this colloidal particle are quite different as compared to just the thermal fluctuations. And how do I model this? I can write down again a Langevin equation for this system, and this K of T is nothing but the protocol which basically makes you do this cycle as shown in this figure. So the KT is a prefix protocol which assumes a certain Carnot or Stirling protocol time dependently over the time. Here also the same thing happens. However, here apart from the thermal noise, you also have active noise. So the thermal noise, of course, is Gaussian white noise, but the active noise may have non-trivial correlations. And even if this K of T, which is time dependent, if you keep it time independent, it's constant, just because of the presence of this active fluctuations eta A, this system is non-equilibrium because the fluctuation dissipation theorem is not satisfied by this active noise, unlike this white noise. Okay, so with this information, I would now like to discuss simple models that we studied in recent years. So now we want to go from a passive engine to an active engine, and what we do is that we don't really worry about the active noise or the statistics of the active noise that is present, what we say is that due to the presence of this active entities in the bath, along with the thermal fluctuations, what changes is just the dissipation constant. Okay, so if you don't have these active noises, you have one dissipation constant, and if you have these active entities, then the dissipation constant is different than what it would be. And I don't really worry about the noise statistics. So the equation would be just this, with a different gamma in different cycles when I go from one temperature to the other, and the system looks something like this. So you have a kind of a protocol which mimics a Carnot or a Carnot system, and in 3 of these branches, so this corresponds to isothermal compression, adiabatic compression, isothermal expansion, and adiabatic expansion. And along these lines, the gamma, the dissipation constant only changes along this line. That means there is a presence of active quantities, and what it results into is change in the dissipation constant. So the equations look something like this. So K of T are nothing but are the functions of this red lines. That's all for these times, and tau is nothing but the total cycle time when I go from K naught along this line and come back. Okay, so that is my time tau as shown over here. And as you can see here, the fluctuation dissipation theorem is satisfied because Zeiti correlation is related to this gamma. However, this gamma plus gamma A comes up here, but the fluctuations due to thermal only has gamma in it, and this is the reason why the system is non-equilibrium and the fluctuation dissipation theorem is broken. So if this cycle time is finite, then we call this non-quasistatic or short time or non-equilibrium. Of course, the system is non-equilibrium, it's non-quasistatic. And you can write down, what you can do is you can multiply these equations by position or the velocities, and you can write down the evolution equations for basically the moments of the position, the variance of position and variance of the velocities. Of course, these are time independent equations, so you cannot solve them completely analytically because of the presence of this time dependent trap strengths. But what you can do is you can, in the large time limit or a long time limit where it takes, is like mimics the quasistatic slow process, or if you choose the cycle time to be much larger than the relaxation times in your system, you can call it quasistatic. You can calculate few things. So these are the definitions of work and heat that I had already discussed. It is now tuned to the problem that we have at hand. So I will not discuss in detail these equations. So they are there, but in the quasistatic limit, you can write down nice equations for the variances in the velocity and the position. They look something like this in different parts of this protocol that I am following. You can also find out the work done in the quasistatic limit and so on.
Rahul, sorry,
yeah.
to interrupt. So someone asked you to clarify the connection between gamma A, so the friction, and eta A, the noise, the active noise.
Yeah. Oh, sorry. So let me go back. So probably I did not say this when I was discussing. Okay, so in this experiment, what was happening is that these bacteria are basically phototactic. So if you shine light on them, their activity increases, and if the light is switched off, then their activity decreases. Okay, so this change in gamma basically mimics the activity in the bacteria. So I'm not really worried about the fluctuations that this colloidal particle experiences, but it's kind of a effect that this particle sees in the dissipation due to the change in the activity from when I go from the higher temperature to the lower temperature. So that's basically the idea. Is this okay?
Yeah, go ahead, I think.
Yeah. Okay, so again, you get this nice expressions for different things. You can calculate work done and heat in the quasi-static limit. Of course, you can check from here that the first law is satisfied, and the change in the internal energy is 0 because you're coming back to the original state because you're doing this this cyclically. You can calculate the work done, and you get a condition that the work done will be negative only if the change in the friction coefficient satisfies this. So the gamma has to be less than the active dissipation that you have, and you can also calculate the efficiency in the quasi-static limit, which is something like this. And if you naively compare it with, let's say, the Carnot efficiency with those temperatures that we have put in, it is much smaller than the efficiency which was seen. Another thing which is important here to note is that when you go from passive engines to active engines, the efficiency, if you calculate of these engines, then active engines tend to outperform the passive engines. Okay, so the efficiency is more in case of active engines than passive engines. And in this case, the reason was given to this non-Gaussian fluctuations that you see in the position of the particle. So if you see here in the passive case, the position of the colloidal particles is basically Gaussian because everything is Gaussian over here. But in this case, the distributions are definitely non-Gaussian, and they have long tails. Okay, so the increase in the efficiency of these engines, active engines, is attributed to such long tails into the system, and such long tails cannot just come because of the change in the this dissipation, but there has to be something in the noise of the active noise that this particle produce, and that's the thing that led us to discuss a few more things. So you can see the total work done as increasing cycle times, and the behavior of the work done in non-quasi cycle time is much different as compared to the quasi static or long time cycle times. The efficiency behaves quite differently when you go as a function of gamma A and so on. So it turns out that though this is a non-equilibrium system, because the friction is changing, the system is still Gaussian, right? Because the fluctuations or the noise that you have is still Gaussian, and it's wide, though it breaks FDR. So now what we want to study is whether we can have this system and study this system with the help of different noises in the system. So we start with the overdamped system because which is easier to Sourabh, you have a question?
Yeah, I just wanted to ask how gamma A was varied in the earlier.
Gamma A was varied in the sense.
So there was
for a given
yeah.
So you mean here?
Yeah.
So yeah, gamma A, when I calculate this efficiency for a certain gamma A, that gamma A is fixed. So a different gamma A corresponds to different experiment.
Okay. But gamma A is something that you are controlling, or you are generating?
Yeah, of course. Yeah.
Okay.
Yeah. Okay, so we start with the overdamped system, which looks something like this. And now you actually have a thermal noise, which is this xi, and an active noise, which is this eta. Okay, and this I1 and 2 will correspond to the isothermal compression and isothermal expansion steps in this protocol. Eta active, we assume that on an average there is no influence of this active fluctuations. So the average eta is 0, but it may have finite correlation times, unlike this delta correlated white noise. So if you start with this, I can write down the general solution of this xi I, and this is the general solution. And since kappa, or this the trapped strength, is a time dependent quantity, this can be calculated for a given function of time, but you will realize that this exponential can have a non-trivial function of time, and this integral in general cannot be calculated analytically. Sourabh, you have a question? Or
Sorry, I think I
Oh,
didn't lower
yeah.
my hand.
Sorry, yeah. So this is the work done with Arnab and one of my PhD student, Rita. So now what we do is to do, at least in case of passive engines, whether we are able to calculate something analytically. So what we do is we define a certain class of protocols for the passive model such that this is satisfied. So since this exponential and the log are inverse functions of each other, we define a certain class of protocols where this kappa t, if it can be written as a derivative of a function divided by its own derivative, then these equations can be solved completely analytically, at least in presence only in the presence of thermal noise. And with eta, it can be solved except for this integral, because the correlations can be non-trivial in case of active noise. So when I write down the sigma t, which is nothing but the mean square displacement, then the first part corresponds to the thermal part, which comes as the temperature of the bath and so on. And the second part comes as an athermal part coming from the athermal fluctuations or the active noises because of the presence of these active quantities. So the simplest protocol which belongs to this class of protocols is nothing but something like 1 by t, and actual protocol which looks something like this. And you can see that this protocol looks something like this. So this corresponds to what is known as the Stirling protocol, and the work done and the heat and the efficiency can be defined in this fashion in terms of those functions, and both of them only depend on this sigma I, which is the mean square displacement of the position. Okay, so so this is the protocol. It looks like this particular protocol that we have used. And in general, this protocol can be as complicated as you want. This is the simplest example that you can have, which belongs to that class of protocols. And if you just have a thermal noise, what you can see is that if I plot the sigma square, or sorry, x square average as a function of this protocol, cyclic protocol, what you see is a very, very similar cycle as you would see in a Carnot cycle, right? So you have this expansion, then adiabatic compression, then isothermal compression and adiabatic expansion, and this cycle repeats. Of course, this is in the steady state after driving the system for a long, long time. Okay, now this is only for the thermal part of it, and we haven't really talked about what happens to these noise-noise correlations. So two very famous examples that one may have are called as the run and tumble kind of a motion of this bacteria. So you have this colloidal particle, and this bacteria or these active particles are surrounding it. So what will happen is that this bacteria may push this particle in one direction for some time, and then it might get pushed in other direction. And once in a while, it may have no activity with this bacteria. There is no collision or pushing and pulling. So if I look at this active noise, it might look something like this. For the time, sometime it is positive, so it gets pushed in positive direction. Then there is no activity for some time, and then after a while, it gets pushed in the other direction by this bacteria, and it will keep on doing this stochastically. And we call this, so this noise can take three states. It can be positive, negative, or zero. Zero means that there is no interaction of this colloidal particle with the external active noise. The thermal noise is always present because it's immersed in this liquid, and it happens at much faster time scales as compared to probably the motion of this bacteria and so on. Another example, of course, this noise, active noise, is clearly non-Gaussian, and which mimics what the experiment was all about. And another example is this active Ornstein-Uhlenbeck process, which has this eta correlation, the active noise correlation, as exponential, but it's still a Gaussian noise, and we call it the Gaussian colored noise. You can show even for this active noise, so-called trichotomous noise, the eta correlation will go as exponential. So now the idea is the following. So as I said earlier, that all these quantities, work and heat, depends on the mean square displacement over here. So basically the correlation the active noises. So if it can be a trichotomous noise, which is completely non-Gaussian, and a Gaussian colored noise with exactly same parameters in this exponentially correlated, because we are only dealing with the moments of the position up to the second, the mean square displacement. We are not looking at higher correlations of these noises, and up to that correlations, both these noises have exactly same kind of a correlation. Only difference is that one of them is non-Gaussian and other is Gaussian, and this is what we see. So for both this, so if I plot the efficiency eta as a function of the cycle time, what I see is it reaches certain value. So this blue graph is basically for the passive engine, whereas there is no active noise acting. And this RT and CN corresponds to the run and tumble and the colored noise. And you can see that I can choose the parameters in such a fashion that it actually outperforms the passive engine, as was observed in those experiments. If you look at the distribution of the position, definitely for the RT, the run and tumble motion, the distributions are clearly now non-Gaussian. And for colored noise, of course, they are Gaussian because the system itself is Gaussian. However, if you look at the standard or the variance in the position, these exactly match with each other, even if the Gaussian nature does not. And it actually gives you the same kind of behavior in run and tumble, or in case of colored noise. So this is the summary of this part of the talk. So we have studied certain Brownian heat engines which are motivated by recent experiment. Active fluctuations play an important part in driving the system out of equilibrium because the FDR is broken. For certain parameter range, active engines show improved performance as compared to their passive engines. And the effect, it's more about of non-Markovinity rather than non-Gaussianity, as we can see over here, because they have exactly same noise-noise correlations and they have a finite correlation time. So we have also have a particular class of protocols for which a passive engine can be completely solved analytically, even for non-quasistatic cycle times, which is not present, I suppose, in the literature. And active engines up to an integral can still be solved completely analytically. Okay, and now I have some time remaining, so I will now discuss a more general statements about these active heat engines, and this is the work done in collaboration with Victor Holubeck at the Charles University. So the idea is the following. So you have a particle, let's say suspended harmonic particle in a bath which contains thermal fluctuations as well as the active fluctuations. And now we are interested in actually recognizing heat in this system. The definition of work is kind of well established even in case of active engines, because it has to deal with the external time dependent parameter change. However, the energy currents in this system are still have some ambiguous definitions. So what we want to do is that you have an underdamped system with active and thermal fluctuations maybe. And is there any way of mapping this non-equilibrium system with active fluctuations to an effective equilibrium system? And the idea why we want to do this is because only if such mapping exists, then the heat currents in this complete system can be termed as thermodynamic heat, and which may have an unambiguous definition of heat. So that is the idea, and the idea is, can we always do it? Okay, so so let me continue with this. So we start with certain Hamiltonian, which is very similar to all the Hamiltonians or the equations that you have seen. You have some part which depends on the position and the momentum, and this KT is nothing but this external time dependent force or the trap strength which changes cyclically, right? So the Hamiltonian will look something like this. I write down the Langevin equation for a constant K, let's say. I look at constant K in such a fashion that I'm looking at at a steady, at a quasi-static case. So this K of T changes slowly, very, very slow as compared to the time scales in the problem. And then I have some force F plus some eta. So this is the external potential. This force is nothing but the memory kernel that you have. So this is the generalized Langevin equation, and this eta is the noise. Okay, and what we also assume is that the fluctuation dissipation theorem is broken. So the eta correlation. So I can have any active noise over here, and that correlation does not necessarily be equal to this gamma T minus T prime. Okay, so we explicitly assume this case, and hence the system is non-equilibrium. Remember, even if this K is time independent, this system is still non-equilibrium because the fluctuation dissipation theorem is broken. The stochastic thermodynamics, as I discussed, I can write about this, and I can have a general confining potential, need not be a harmonic potential. So what we can write down is the first law of thermodynamics, and sigma x over here is nothing but the average of x to the power n, or the average potential energy that you can see with n, which confines this particle. So in our case, in earlier case, it was harmonic. So n was basically equal to 2, and this is nothing but the mean square velocity, average mean square velocity. Okay, so Q dot in this case, when I have work and heat, is thermodynamic heat only if there exists an engine with an effective equilibrium bath with same energy fluxes. Okay, so I can define these things. I don't have too much time to go through it. So what we need for having this correspondence or mapping is two theorems. One is the equipartition theorem, which tells you the average kinetic energy is related to your temperature. And this temperature need not be the temperature of the bath, but it can be an effective temperature, which contains the thermal part as well as the active part. And another is the virial theorem, which tells you that twice of the average kinetic energy is related to the potential energy in this potential in this fashion. And the T effective that exists is basically nothing but the equipartition theorem that you get. And T effective is the temperature of the equilibrium baths, the effective equilibrium baths. Okay, so for that, what we show is that this T effective can only exist. So you start with this equation, and you multiply it with the position, and you can write this down in this nice form. And in the quasi-static case, this part will go to 0, and you can have sigma v equal to k sigma x only if this part, which is the total force plus the noise, which is force due to the bath or the virial due to the bath, and if it is completely uncorrelated with the position of the particle, then only this T effective can be defined. So this is the condition that we get. So non-equilibrium to equilibrium mapping or effective equilibrium mapping is possible if the contribution of the bath to the virial is 0. Okay, so this force plus this noise is completely uncorrelated with the position, then only such an effective mapping exists. So this is again how you do this, but I will, in 2 minutes, I will discuss a few important examples of these active Brownian particles, which are very famous and popular. So one of them is the active Ornstein-Uhlenbeck process, where the noise-noise correlation is the exponentially correlated. So in this case, if you define these quantities, you will be able to show that this x into eta correlation is actually non-zero. Okay, so for such a simple process where you have this active Ornstein-Uhlenbeck process, the effective temperature in case of underdamped system does not exist. Okay, so it's a very popular system used to mimic or model active Brownian particles, and for that you don't see any effective temperature. Another example, which is very, very similar to the problems that we discussed earlier, is that you have an active noise which is, let's say, exponentially correlated, and another part which is the thermal noise. Okay, and of course eta correlation is definitely not equal to this gamma t, because we have assumed that the fluctuation dissipation theorem is broken. And then you can find out a condition under which a effective temperature can be defined. Okay, so you have to fine tune these parameters, gamma, gamma1, pha1, and all that. They are quite general in nature. And under this condition, a T effective exists. That means basically the average of the kinetic energy gives you the same temperature as the average of the potential energy. And that temperature is nothing but this T effective. This is important because in such cases, what you can do is you can recognize this T effective and T effective in case of, let's say, high temperature and low temperature along these cycles, let's say in Carnot cycle and so on. What it means is that it's an effective equilibrium system, and you can use effectively the thermodynamics that we know for equilibrium systems, and basically it might reach Carnot efficiency or even the Curzon-Hurlbon efficiency and so on. So these are some simulation and other results. Okay,
Right.
so I just want to say that only where these two graphs coincide, there the effective temperature can be defined for such system, and it doesn't exist anywhere else. So these are the conclusions that why we want to study this mapping and so on. So I will not repeat because they are already there. And let me thank you. And if you have any questions, thank you very much.
Thank you very much. Yeah, so we are slightly late, but we can take a couple of questions. So you have also quite a number of comments in the chat, so probably we won't have time to go through that,
Okay.
but you can answer them later. So Sanjeev, you can go.
Yeah, this Rahul, at some point you showed this average work done as a function of this gamma A, right?
Yeah.
Yeah, I think first part of this, and
yes,
for certain tau you had a minimum, and then
yeah, let me go back to that.
Yeah, that one. Yeah,
that's right.
So is there a tau C that minima disappears, or the minimum is there for high gamma A for large tau?
Oh, so you go even.
No, I'm asking, like, see, for tau equal to 20, there seems to be a minimum,
yeah,
right?
It's here, right?
Yeah, but for example, if I go to tau equal to 100 or 500, is there a minimum, or it's not there?
No, it's not. It kind of saturates after a while. So that you can actually see from this, because yeah.
So is there a critical tau where the minimum disappears?
Okay, for that you have to know the this W as a function of complete. You need to know it as a function of time. This tau, right? And you will be able to calculate it by taking the derivative with respect to tau and equating it to 0. But the problem is that in this case we don't have an explicit expression for W. We can only find it in the quasistatic case, not for general tau. But numerically, of course, you will be able to see whether you get this minima.
So is it there or not there?
I haven't checked. Probably, okay. I don't know.
Okay. Yeah. Okay, thank you.
Yeah. Okay, so the next question. So Ayan, can you unmute?
So can you hear me, right?
Yes.
Yeah. So no, the protocol in your first part. So does your efficiency plot, does it depend on the the values of K1 and K2? Because
yes, of course it does. Yeah. So what you can do, let me go back to this. So it also where is that? Yeah. So of course, I can change the values of K1 and K2 in some fashion. And it turns out that if you allow the particle, if this particle can access large positions, that means that your trap is actually very, very shallow, right? Then your efficiency will depend on it. So if it can access these long, extremes, which probably may not be possible if the trap is very sharp. If you allow that it accesses this, then the efficiency depends on that. So probably you get higher efficiency. Is this okay? Yeah, because see, I mean, all your work done and heat depends on the mean square displacement. So if the mean square displacement is large, your efficiency probably will also increase.
So I had in mind, like depending on this K1 and depending on the value of K, the stationary state of these active particles are completely different, right? Somewhere you get a Boltzmann stationary state, or somewhere you get these.
So that actually, okay, so I didn't discuss this, but this depends on this parameter. Oh, sorry, I'm going back. Yeah, so it actually depends on this parameter beta, which is nothing but the measure of competition between the persistent time between these correlations of the active noise and the confinement. And in some cases, if beta is greater than 1, I think in this case, then you get completely Boltzmannian kind of a behavior. And in other cases, you get a trimodal distribution, which is obvious because the particles are pushing it in 2 directions, as well as there is a state with no activity. Right? So that's basically this beta corresponds to.
Okay.
And you get a different behavior if you change this this beta. Does that satisfy?
Okay, so the last question, Sarah, so go ahead.
Yeah, thank you. So you concluded on that the non-Markovianity is more important than the non-Gaussianity.
Yeah.
And I was wondering if you have looked at the question whether a passive non-Markovian bath could also boost the efficiency, or if it only goes if it's non-Markovian and active.
So okay, so this is in the preparation. So we have been working on this. See, the problem is that in this case, you can actually compare a passive engine with an active engine by just switching off and on the active noise. But when you have a memory, so you're saying that the passive engine is where the fluctuation dissipation theorem is satisfied. And okay, so that we haven't checked, but probably it will boost the efficiency there as well. You can always find certain, yeah.
Okay, thank you.
Yeah.
Okay, thank you very much, Raoul.